This is a regular pentagon. The question is, in how many ways can a regular pentagon be divided into 3 triangles if different orientations are counted separately? This is a simple problem. We can just count all the solutions to answer this question. We can divide the pentagon like this, and like this. In total, there are 5 ways to divide a regular pentagon into 3 triangles. But what if we look at different shapes? For example, a square or a hexagon. First, we need to transform our question. Let's replace the pentagon with the polygon with n plus 2 sides and replace the number of triangles with n. Now, let's try to answer the question for a square. Square has 4 sides, so n plus 2 is equal to 4. So we need to find in how many ways we can divide a square into 2 triangles. There are only 2 ways to do this. Let's also look at the hexagon. N plus 2 in this case is equal to 6. So we need to divide the hexagon into 4 triangles. There are 14 ways to do that. Now let's compare all polygons. Starting with n equal to 1. N plus 2 is equal to 3, so we have a triangle. And there is only one way to divide a triangle into a triangle. When n equals 2, we have a square. There are 2 ways to divide a square into triangles. For pentagon, there are 5 ways. For hexagon, there are 14 solutions. When n is equal to 5, the number of ways is already equal to 42. This sequence of numbers is called the Catalan numbers. From this example, we can see that the first 5 Catalan numbers for n greater than 0 are 1, 2, 5, 14 and 42. The Catalan numbers were first discovered by Leonhard Euler, who worked on the problem of counting the number of triangulations of a polygon with n number of sides in 1750s. However, they were named after Belgium-born mathematician Eugene Charles Catalan that became interested in the problem in 1838. Catalan numbers are used to solve many interesting problems in combinatorics, probability theory, computer science and other fields. This is a valid parenthesis expression. It consists of 1 open parenthesis and 1 closed parenthesis. If we reverse the order, the expression is no longer valid, because we can't close the bracket and then open it. We can expand the expression by adding more parentheses. The question is, how many ways are there to create a valid parenthesis expression with n right parentheses and n left parentheses? To solve this question, let's consider the right parentheses to be plus 1s and left minus 1s. For the expression to be valid, the partial sum of the expression always must be greater or equal 0. We can visualize this using Dyck paths. A Dyck path is a mountain range with n upstrokes and n downstrokes that all stay above a horizontal line. Let the plus 1s be the upstrokes and minus 1s be the downstrokes. The expression will be valid if the path never goes below the horizon. We can see that the question of how many ways there are to create a valid parenthesis expression with n right parentheses and n left parentheses has the same answer as the question how many ways there are to create a mountain range with n upstrokes and n downstrokes that never go below the horizon. Surprisingly, the answers to both of these questions are the Catalan numbers. From the example with triangulation, we know that the 4th Catalan number is 14, so there are 14 ways to create a valid parenthesis expression with 4 right parentheses and 4 left parentheses, and there are 14 ways to create a Dyck path with 4 upstrokes and 4 downstrokes. We know those numbers from the previous example, but what is the general formula for the Catalan numbers? Let's consider another problem. We have a number plane. The question is, starting from point 0, 0, how many ways, in other words, lattice paths, there are to get to point NN by only going right or up and not crossing the red line? The valid path would be, for example, right, right, up, right, up, up, right, right, up, up, right, up. Let's consider that going right is plus 1 and going up is minus 1. To always be below the red line, the partial sum of plus 1s and minus 1s must always be greater or equal 0. From this, we can see that this question has the same answer as the previous two problems. So, if we find the formula for getting the number of different paths that are below the diagonal, we will also get the answer to the previous questions and the general formula for the Catalan numbers. To calculate the number of paths that go below the diagonal, first we need to calculate the total number of ways that we can get from point A to point B, and then subtract the number of paths that go above the red line. To calculate the total number of paths, let's say that n equals to 4. So to get to the point 4, 4, we have to go 4 times up and 4 times right. The shape of the path depends on the arrangement of our steps. We can arrange our steps like this: right 2 times up, right 2 times up, and 2 times right. So, to calculate the total number of paths, we just need to figure out how many ways there are to arrange these terms. So we have 8 steps in total, and we choose how to arrange the 4 right steps. The other steps will be up steps. So, the total number of paths is equal to 8 choose 4. N is equal to 4, so the general formula for calculating the number of total paths to get to the point nn would be equal to 2n choose n, and that is equal to 2n factorial over n factorial times n factorial. Now we need to figure out how many of these paths go above the diagonal, and there is a brilliant way to do that. Let's draw a path that crosses the diagonal. Now let's look at the first point of the path that crossed the line, and let's make a mirror image of our path after that point. So after the point we went up, so now we will go right. Then we went 1 right, so now we will go up. Then we went up, so now we will go right. Then we went 2 times right, now we will go 2 times up. We got to point n-1 and plus 1. Let's take another path and do the same. So this point is the first point that is above the line. So after this point, we make a mirror image of our path. And what's interesting is we get the same point as the previous time. In fact, every path after this procedure will go to the point n-1 and plus 1. So now we know that the number of paths that go above the diagonal is equal to the total number of paths that go to the point n-1 and plus 1. So it's equal to 2n factorial over n-1 factorial times n plus 1 factorial. Now we can answer our question. We just have to subtract the number of paths that go above the diagonal from the number of total paths. This is the formula for the number of total paths that never cross the red line. But we can simplify this formula. We can pull out front 2n factorial divided by n factorial times n-1 factorial, and in the brackets we are left with 1 over n minus 1 over n plus 1. Now let's subtract the terms in the brackets. So the common denominator is n times n plus 1. And in the numerator we have n plus 1 minus n, so we are left with just 1. N times n minus 1 factorial is just n factorial, and n plus 1 times n factorial is equal to n plus 1 factorial. This is the formula for the Catalan numbers. The nth Catalan number is equal to 2n factorial divided by n factorial times n plus 1 factorial. We have the answers to all questions. The question about the triangulation of the polygons, the number of valid parenthesis expressions, the number of Dyck paths, and the number of lattice paths that go below the diagonal. The Catalan numbers are also used in many other problems. For example, this problem. In how many ways we can tile a staircase with height equal to n, with n number of rectangles? The answer is also the formula for the Catalan numbers. The Catalan numbers have a lot of other uses, and there are numerous counting problems in combinatorics whose solutions are given by the Catalan numbers.